Norton theorem, it states that any two-terminal active network containing voltage sources and resistance can be replaced by a constant current source and a parallel resistance. Well, this constant current source is what we call the Norton current, or you call it the short current, circuit current. Now, the parallel resistance is what we call the Norton resistance, Rn. Now, what are the steps we use to solve the equation using the Norton theorem now? Well, the first is to remove the load resistance and short circuit that part. I will illustrate that when I'm solving a question. And then the next is to compute the short circuit current, ISC, short circuit current, which is also known as a Norton current. Then again, remove all voltage sources and replace by short circuit, and all current source and replaced by open circuit. Find the resistance Rn of the network as looked into from the given terminal, exactly the way we do our Thevenin resistance. Essentially, we do Norton resistance. Then the current source ISC or IN is put in parallel with the Norton resistance, and this is what we call the Norton equivalent circuit. Let's take a question now. Look at this question. The question says, using Norton theorem, find the current flowing through the 12 ohm resistor. This is this. So solution, we are following the step 1 now. Remove the load resistor. Load resistor is the resistor you are looking for the current flowing through it. So I'll remove it. Okay. What I'm looking for here now is ISC or IN. This is IN. Now you can use any other means to get your IN. You can use mesh, you can use any method. Well, for me, one easy way to get your IN is that IN is equal to 120 over 40 plus 180 over 60. The reason is because, you see, this is supplying current in this circuit. Current coming from here will go here and flow through here. It should not divide when it gets here. Why will it not divide? You know, let me assume this current coming from here. When current gets here, it has two parts to follow, here and here. But looking at this part, there's resistance here. Look at this part, no resistance here. Current will follow the path of least resistance. So current will, all the whole current will flow down to this part and nothing goes in here. And the current coming from here too, when it gets here, nothing will flow here. You just go down here. So that's why it is 140 over 120 over 40 and plus 180 over 60. And that will just be simply 3 plus 3, which is 6 ampere. You can use your mesh to solve this question. So since maybe you are conversant with mesh, okay? So let's go now using mesh to solve this question. This will give us like this. For the first, it's going to be 120 minus 40 I1 equal to 0. And that will simply be that I1 is equal to 120 over 40. And that's 3 ampere. Again, we can see that minus 60 I2 minus 180 is equal to 0 for this. This is for mesh 1. For mesh 1. and this for mesh 2. And this will be that I2 is equal to 180 over minus 60 minus 3 ampere. Then we can now say IN is equal to, IN is same direction with I1. So that's positive I1. It's in opposite direction to I2. The IN is opposite direction to I2. That will be minus I2. I1, 3, minus I2, minus 3. And that will be 3 plus 3. That's 6 ampere. So we are done solving for our IN. The same with what I got using the other method. So we are done with this now. The next is to get our Rn. Okay? So all voltage sources now will be short-circuited. So short-circuiting means remove and draw a straight line there. Don't open it. And then the part where the resistor is will be open circuited. So it's open now. And then all voltage short-circuited. So we have this now. This is 40 ohms and 60 ohms. Okay, and they say look from this open part. You see these two, how they are, either parallel or series. But like I said, that for me, I don't like looking that way, because for me it's more or less like maybe I don't see anything. But there's where I do mine. What I simply do is to say, assume current is coming from this part, you remove its resistor. When current gets here, it is split. When the current gets here, it is split. It's an assumption which is not true, but when it works and it gets me what I'm supposed to get, the current is, the some will go here, some will go here. That made these two parts parallel. So the total resistance will be these two resistors in parallel, and they are the last two resistors. So my Rn will be equal to 40 ohms in parallel with 60 ohms. And you know, the short method of getting two resistors in parallel will be product over sum. 40 times 60 over 40 plus 60. This will give me 2,400 over 100. That's 24 ohms. Another way to do this is to say 1 over Rn is equal to 1 over 40 plus 1 over 60. And you get the same answer with what we have here. So that's about that. We've gotten our Rn and we've gotten our In. The next thing to do here is to simply put our Norton equivalent circuit now. And that will be the constant current source, which is Norton current, in parallel with the Norton resistance. And then lastly, with the load resistance. Rn, and In. Our In is 6 ampere, Rn is 24 ohms, and Rn, the one we remove, is 12 ohms. Now, we can now use current divider rule to get the current flowing through, this is the load, sorry, RL. So that's what I'm looking for. Our IL, using current divider rule now. Current divider rule. IL will be equal to Rn over RL plus Rn times the In. And that will simply be Rn 12 over 12 plus 24 times 6. This will be 12, 1 over 3 times 6, which will be 2 ampere. Because this is 12 over 36, that's 1 over 3 times 6. That is 2 ampere. So that's the answer for this question. Draw the Norton equivalent circuit and obtain the current flowing through the 10 ohm resistor. Okay, so let's solve this question now. This is a 10 ohm resistor. Remember, first of all, we'll short circuit the load resistor. And that will be a way to get our In. So I'm looking for our IN. Okay, this is 40 ohms, 12 ohms, and 60 ohms. So to do this now, we can employ the mesh I1 and then I2. We can't use a simple trick here now because current coming from here must split. There's a resistance here, there's a resistor here. So let's go and solve for using our mesh. Now this is going to be 120 minus 40 I1 minus 12 into I1 minus I2, which is equal to 0. This is going to be 120. This is for my mesh 1. Students often think that because this is Norton theorem, I cannot use mesh in getting something else here. That's wrong. Say maybe two theorems interwoven here. No, it's not a problem at all. So anyway, you can use proposition to solve this question. It's not a problem. Minus 12 I1 to get minus plus 12 I2 equals 0. So this is going to be 120 being equal to 52 I1 minus 12 I2. So you can use proposition to still get this IN, no problem. This is equation 1. And then for mesh 2 now, we have minus 60 I2 minus 10 I2 minus 12 into I1 minus I2 minus I1 equals 0. So this will be minus 60 I2 minus 10 I2 minus 12 I2 and then plus 12 I1 equals 0. So this will be 12 I1 minus 82 I2 equals 0. This is my equation 2. So simultaneously solving equation 1 and 2. That will give us, let's solve that now. So we have 52 I1 minus 12 I2 equal to 120. And then again we have 12 I1 minus 82 I2 and then 0. Our I1 is given as 2.39 ampere and our I2 is 0.35 ampere. So looking at this now, we can say hence or therefore IN is the I2, which is 0.35 ampere. Next is to get our RN by removing all voltage source by short circuiting. So we're doing that right away. $40 ohms, 60 ohms, and 12 ohms. Okay, like I said now, I'm looking for the RTH here, RN here, sorry. So assume current is coming from it. That's what I used to assume. To get here and split, some will go here, some will go here. These two parts are in parallel. So my RN will be 40 in parallel with 12 ohms. 40 ohms in parallel with 12 ohms. And that itself in series with 60 ohms. But when I combine this, it will not be in series with this. And that will be 40 times 12 over 40 plus 12 plus 60. Let's get that now. 40 times 12 over 40 plus 12 plus 60. That will be 69.23. So the next will be our Norton equivalent circuit. Norton equivalent circuit. Okay? So that will consist our In in parallel with Rn in parallel with RL. So this is our RL, Rn, In. So our In is going to be 0.35 ampere. Rn is 69.23. In is the 10 ohm resistor. RL. So we'll now use our current divider rule to get that now. So let's do that right away. So our IL is simply equal to Rn over RL plus Rn times the load times the source current In. So Rn 69.23 over 69.23 plus the load, which is 10 times 0.35. 69.23 all over 69.23 plus 10 times 0.35, 0.31 ampere. So that's that. Using Norton theorem, calculate the current flowing through R, this R. Well, quite easy. First of all, short circuit the load resistor. Would have this. Okay. So as a mesh now, this will be 5 minus 3I1 minus 14 into I1 minus I2 equals 0. This will give me 5 minus 3I1 minus 14I1 minus plus 14I2 equals 0. This will be 5 being equal to minus 17. That's 17I1 minus 14I2. Equation 1. That's for mesh 1 though. Now, for mesh 2, it's going to be minus 5 I2 minus 9 into I2 minus I3 minus 14 into I2 minus I1 equals 0. This is going to give us minus 5I2 minus 9I2 plus 9I3 minus 14I2 plus 14I1 equals 0. And so this is going to give us 14I1 rearranged, minus 5 minus 9, that's minus 14, minus 14 minus 14 will give us minus 28. I2 and then plus 9I3 equals 0. So this is equation 2. And then for mesh 3 now, and so this is going to be minus 9I3 minus I2 equals 0. That is minus 9I3 plus 9I2 equals 0. This is going to be 9I2 minus 9I3 equals 0. This is equation 3. So we're going to simultaneously solve this now. Let's solve that now. So I'm going to use my calculator. to get this simultaneous equation. So revolving 3 unknown now, and that would be 17, yeah, minus 14, yeah, 0, yes, and then 5 for the first. The second one is 14 minus 28 plus 9 equals 0. The last one is 0, 9 minus 9 and 0. So we have our I1, which is unnecessary for me, which is not needed for me, 0.743. I2, 0.551. I3, 0.551. So I can simply say that IN is same as I3, which is 0.551 ampere. Now, the next thing to do here now is to get our Rn. Our Rn will deactivate the voltage source. Okay, so from here now, our no current is coming from here. When they get to it, is split. Some will go in here, some will go in here. And that which goes in here, we get to this junction again and then split again. So some will go into this part, some will go into this part. These two are in parallel. So I can say in the first case, 3 ohms in parallel with 14 ohms. If we do that, that will be 3 times 14 over 3 plus 14. So 3 times 14 over 17. This is 2.47 ohms. That reduces the circuit to this way. I've combined these two to be this 2.47, and this is 5 ohm, and this is 9 ohms. These two now, if current is coming from here again, it is split. Some will go in here, some will go in there. These two are in series. So how do we go about that? Let's clean this part now. So that would be 2.47 plus 5 ohm, and that is 7.47 ohms. So that is reduced to this now. Our RTH will now be 7.47 in parallel with 9 ohm. And RTH will simply be 7.47 times 9 over 7.47 plus 9. Since if current is coming from here to split, these two are in parallel now. 7.47 times 9 divided by 7.47 plus 9. 4.08 ampere. We cannot draw a Norton equivalent circuit now. Our IN, RN, and RL. RL is a 1.5 ohm. Rn is 4.08 ohm, and our In is 0.551. So we can say that IL current flowing through this, which is Rn over RL plus Rn times In. Rn 4.08 over 1.5 plus 4.08 times the 0.551. That will give us 4.08 times 0.551 divided by 1.5 plus 4.08. That's 0.4 ampere. So that's that about that.